Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll more closely examine the interference patterns of pairs of acoustic sources, and we'll learn how phase influences these trends.
So let's get started. We've just found that in a geometric far field, which is when we're very far away with respect to the characteristic dimension of the source pair, the beam pattern defines the angular distribution of the acoustic pressure amplitude. The origin of this distribution is due to interference. Constructive interference is when the waves add up. Constructive interference occurs at broadside especially, when theta is equal to 0 degrees. Under these conditions, we have the case where the sources radiate sound with an integer number of wavelengths in between them. At broadside, this integer number is 0 wavelengths in between them. But for off-axis field point locations, this occurs, for instance, as the case is shown here, where 2 wavelengths are equal to d sine theta. In that instance, the wavelengths are exactly in phase. This would be a case given the frequency and wavelength lambda involved, we would have a side lobe for this angular location. The alternative, where nulls and nodes occur, this is destructive interference. It is due to the fact that the waves are canceling out. Now take, for instance, we have 3.5 wavelengths are equal to d sine theta. In other words, they're equal to the angular distance between the sources with respect to the field point. In this case, one source has a negative value at an instantaneous location in space, whereas the other has a positive value. So this would be the case of creating nulls, also called nodes. These interference phenomena are exacerbated for an acoustic source called the doublet. If we take our original point source pair and cause one of the sources to oscillate 180 degrees out of phase, we have the doublet. The characteristic dimension remains to be the distance d, which is the distance between the sources. Now, considering the geometric far field, the acoustic pressure for the doublet, if we run through the same analysis that we did for the point source pair, we have 2 times j, a on r, e to the j, omega t minus kr, multiplied by sine of kd on 2 sine theta. Before, our beam pattern was a cosine of kd on 2 sine theta, and now it is a sine of kd on 2 sine theta. How do we compare this point source pair, whether the point sources are in phase or out of phase? We're already familiar with our in-phase point source combination. They're maximized at broadside when theta is equal to 0, and sound delivery to the field point is minimized when we have the following condition: d sine theta is equal to 2m minus 1 divided by 2 times lambda, where m is an integer, 1, 2, 3, and so on. So for instance, when m is 3, our numerator is 6 minus 1 divided by 2 times lambda, so 5/2 of a wavelength. Alternatively, if m was 2, we'd have 4 minus 1, which is 3. 3 divided by 2 is lambda, is equal to d sine theta, which was the example that we saw previously. Now, for the case where the point sources are out of phase, we know our acoustic pressure amplitude as seen from the prior slide. The maximum sound delivery now occurs when theta is equal to 90 degrees. This is called Grazing Index. When we consider a case where we're looking at sound against the line parallel to the sources, we know this occurs by applying 90 degrees to our acoustic pressure amplitude shown at the left. In this case, sound is minimized when d sine theta is equal to m theta, where m is equal to 1, 2, 3, and so on. In the case for the in-phase point source combination, this criteria was actually the maximizing approach, whereas for the out-of-phase point source combination, this exactly eliminates all of the sound delivery due to perfect destructive interference. Let's study the out-of-phase point source combination one step further. When we have a small doublet that's acoustically small, in other words, KD is much less than 1, where this is KD is equal to 2 pi, D on lambda is much less than 1. We call this doublet a dipole, or an acoustically small doublet. There are many practical acoustic dipoles that we experience day to day. Rotating fans, where we have positive pressure and negative pressure on the different sides of the blades. As the blades spin, we have positive pressure, on the back side, negative pressure. This creates a dipole effect, where one side of the source has positive phase, the other negative phase. Air acoustic vortex shedding, especially over spoilers and around A pillars, B pillars, and the sunroof. Tuning fork oscillation also is an acoustic dipole. And unbaffled loudspeakers, where we have a loudspeaker that's going to generate sound, and it creates positive pressure on one side, and on the back side that's unbaffled, we've got negative pressure. So itself has a positive phase, and on the back side has a negative phase, just like the conventional acoustic doublet and dipole.
Now we're going to experience an acoustic dipole. Let's check out our tools. Here we have a loudspeaker cabinet and an 8-inch subwoofer. We have a sound level meter here for reference. We'll drive the subwoofer at 60 Hz and then remove it from the cabinet. As an unbaffled loudspeaker, it will act like a dipole, radiating positive pressure from one side, while the other side creates negative pressure.
So let's summarize what we have learned. We've now investigated further to gather intuition regarding interference from coherent sound sources when we're considering far field locations. We found that interference is due to the number of wavelengths that exist between the parallel paths that the sounds travel from each source. And for in-phase sources, a major lobe occurs at broadside, whereas for sources that are out of phase, the node occurs at broadside. There are many practical examples where we exhibit this interference pattern for in and out of phase sources.
That's it for this video. In the next video, we'll generalize this analysis for point source combinations.